It is? Oh, perfect. Well, good morning. It's a great pleasure to be here. I'm a professor of physics in Lisbon, Technical Lisbon, but I'm also in Copenhagen. I came from Copenhagen. It's really dark, so I really appreciate the fact that I'm here. Thank you to the organizers for giving me some sun, but also for giving me the opportunity to talk about what I think is the topic for the next few decades, okay? So I was asked to talk about, I was given total freedom, and I was asked to talk about gravitational wave physics and the impact on fundamental issues. So I'm going to go a bit off the usual track, maybe, and I'd like to talk to you about the things we don't know and that we might learn using gravitational wave physics. And that relates mostly to some of the things we know goes wrong with gravity, most especially strong field gravity, in some definition of what this means. I'll go into that a bit later. So I'll start by giving an overview about black hole physics, the standard picture. I hope you heard half of it, but if you haven't, it's also okay. And then I'll try to tell you in the next few days, you know, how can we learn more about gravity using gravitational waves in the future. I was listening to the very interesting talks on dark matter physics, and there's a question for people like me, which is what happens if dark matter only interacts gravitationally? You know, what exactly, how can we learn about it? And I'll tell you that black holes are really possibly the only tool in some mass range to understand this. They are able to condensate bosonic degrees of freedom outside the horizon, and these guys can work as lighthouses. This is called super radiant effects, and I'm going into some detail on this on my third lecture. I prepared I'm a slow guy, okay? And I'm going I'm going slower than usual because I got poisoned by garlic of all things. But because I also would like you to know as much as when I finish the lectures. Okay, so I prepared a few notebooks in Mathematica. I don't know if you got them. If you haven't, it's okay. I can send them to you. Who here usually works with Mathematica in their career? Perfect. So some of these notebooks, I started them in my PhD, okay? My PhD was about gravitational waves in black hole physics. I was doing stuff by hand, and you know, after a couple of weeks doing the same things and getting different outcomes, I thought, well, okay, let me be a bit more professional. And so more or less, when you do soft numerics, we now use symbolic manipulators like Mathematica or Maple or some other thing. And most of the stuff I'm going to discuss here are soft numerics. Of course, if you want to be a bit more evolved, then you want to do the full set of nonlinear Einstein equations in the computer. I don't have anything on that here, but we can also talk about it. And finally, I don't know if this is going to work. I'm just going to scroll down as time goes by, okay? Please ask questions, because if you don't, it's almost a waste of time, yours and mine. So just interrupt me, and if I say something that's wrong, just shout, or if it's not clear, also just ask me. So there's going to be 4 lectures. The first is on black holes as kind of a fixed arena. Okay, I'm going to tell you all the interesting things about black holes. 3 things actually. They're very simple. All there is to know on the black hole exterior, we know it. We have no idea what's going on black hole interiors, and we have no idea of how to get there. That's basically more or less the morale. And the final item is we know how to extract energy away from black holes, and I will continue this in the third lecture. The second lecture, I would like to tell you how we study gravitational waves on black hole spacetimes. You know, the standard treatment of gravitational waves takes a flat Minkowski spacetime. You linearize that stuff, and you see 2 degrees of freedom, like in Maxwell theory. You know, just in the way that you look at sound waves here in this room, you just linearize the Navier-Stokes equations and you see something happening. I would like to take a different route for this. I'll just start with a curved spacetime, and I'll try to do the same and hit this spacetime and see what happens there. And then, so this is really the things, the juice of what I want to tell you. The third and fourth lectures, I would like to build on this, on the first two, and start telling you what's happening now. How can we use black holes as detectors of new particles? How can we use black holes to test general relativity in a regime where it hasn't been tested? Okay. Very good. So lecture one, I'm going to tell you very briefly about black holes, uniqueness, and no-hair properties. What happens in stationarity? How exactly does matter move on black hole spacetimes? What's the main features of this motion? And then, once you add spin, what exactly new do we get from spin? Okay, and mostly I'd like to tell you about the ways to extract energy away from black holes and ways to test what I'm going to call the cosmic sensor. Also, I added a slide last night because somebody asked the question about how exactly we form primordial black holes. How do we think about black hole formation away from standard collapse of stars? So I have something to say about that. That's been going on in the last, well, many years. There's references in the PDFs. They range from different levels. Classical stuff. If you want to know everything about the field, you might want to read Maggiore. It's a wonderful set of 2 books on gravitational waves. Most, but not all, of the things I'm going to say are there, okay, to some extent, to some level of detail. You also want to read Poisson and Will. It's a fantastic book about all the things we should know about GR and classical gravity. And of course, then there's more specialized works like the living reviews on black hole uniqueness results. Of course, I always throw a couple of my own. And then some attempts at destroying black holes. It started with Bob Wald in the 70s, and it continued, until, well, actually it's going on. Attempts at destroying black holes using full nonlinear Einstein equations. You just take, I'm going to show you an example. You just take 2 black holes, you smash them together, and you try to get rid of the horizon. That's really the stuff preventing you from looking inside black holes. And of course, I'll try to prove this Cristóbal result on the irreducible mass, how much energy you can remove away from a spinning black hole. Very good. So my fundamental object, for those who are not familiar, you don't really need to be familiar, but it's going to be a metric. So I'm given a manifold, a space-time, and there's some way that I can measure intervals, okay? That's the metric. So you have there your line element. That's basically everything we want to know. We need to know here. We take the metric and then we build some tensor or tensor-like objects. For example, the Einstein tensor, and this gives me the field equations. I'm not going into how you get from one to the other. I'm just going to assume general relativity is correct. So the field equations are Ricci tensor and Ricci scalar. They combine to give you the matter content. Geometry on the left-hand side, matter on the right-hand side. I will always be working in units. It's a handicap of the stuff I've been doing for many years. So unfortunately, I always set G and C to 1. I'm sorry for this, but it's so much trouble to go back and put G and C's where I should. So in these units, mass and length and time all have the same kind of dimensions, okay? So it's really standard to say that the sun, it's 10 to the 30 kilograms, but you can also express it as 1.5 kilometers, or, can you see this? No. Wait. Or 10 to the minus 6 seconds, okay? You just add G's and C's in a way that you get seconds, time or length or whatever. Okay, and this gives you an idea. So if you're thinking about LIGO, if you're thinking about gravitational wave stuff, if you're thinking about things where the dynamics of black holes are relevant, and you have a one solar mass black hole, you should always bear in mind that these are the scales. Okay, so if you have a black hole relaxing, think about scales of microsecond. That's the thing. Okay. And if you think about a stellar mass black hole, well, then you should think about scales of 1, 2, 3 kilometers. Okay? Now, the field equation, so that, of course, if you're trying to build, to solve the field equations, G mu nu equals C mu nu, nobody knows how to solve this. Okay? It's really, really tough. Of course, we have some very specific examples for the last 100 years, but even when you're solving the set of partial differential equations numerically, there's a lot of input that needs to go into there regarding symmetries, time dependence, and so on and so forth. Okay. Even specifying the matter, it's really standard to say, oh, I'm going to look into stars that are composed of a scalar field. Well, what exactly is that scalar field? Why are we using a scalar field to model the stress tensor? Okay. I'm not going, I think, to go through all of those complications. I'll just start building stuff in vacuum. Okay. To see if I can build stuff in vacuum. So I'll just set T mu nu equals 0. And if you open the notebook, one of the notebooks that I sent, okay, there you go. This was the stuff I did when I was in my second or third year of PhD. After, trying to fluctuate the Einstein equations and failing miserably, that's what I started to write. I am sure that there's packages now, Exact and many others, which are way superior. Okay, so don't sneer at me. But you know what's happening in this stuff. You see things. There's no magic box there, okay? And so what goes in is, well, the space-time metric. So you assume that it's spherical symmetry, so all of the off-diagonal elements are set to 0, okay? Just by assumption about the spherical symmetry. And I even allow for time dependence in these guys. I choose coordinates such that I'm actually using the areal radius, stuff that gives me the area of spheres, okay? Hence the last two guys, these guys, look so nice, r squared and r squared sine square of theta. And that's it, basically, okay? Then you go through, you calculate the contravariant metric tensor, you define your set of your coordinates that you're using, and then you calculate Christoffel symbols, the Riemann, the Ricci, and so on, okay? And then the field equations. So you just plug the metric and you output G mu nu. That's what you do, okay? And that's usually a set of second order differential equations in time and space, okay? Because you only have up to second derivatives, which is nice. We can do physics with second order quantities. We can't do physics with higher order PDEs. Okay? The time evolution is not well defined usually. There's some exceptions. And that's it. Okay? And if you go through all of this is quite simple. It's a few seconds. Just shift enter and there you go. Very good. Let me see if okay. So when you do this, you will realize that in spherical symmetry, the time dependence is really relevant. Okay, this is known as the Birkhoff theorem, and the general solution looks like that. There's a constant, of course, when you solve the field equations, you don't, I call this m because I know this is the space-time mass. But when you're solving them, it's really just a constant of integration. Okay, then you need to look at motion of things to have some kind of idea of a Newtonian limit of your equations. Very good. This is my spherically symmetric solution of the field equations. Let's look a bit at the solution. There's two issues here, okay? Two problems. The first problem is that this guy blows up, okay, at r. So r is my radial coordinate. Again, notice that this is an aerial coordinate. Okay, it gives me the area of two spheres. It blows up at r equals to m. Again, g equals c equals 1. So actually, this is 2gm over c squared. Okay, just to be on the same page. But also, it blows up at r equals 0. Okay, so we should try to understand both of these points and what happens to my solution. Is this a star? Is it possible that this describes a star, or is it really something else? Now, to understand this, especially, not only, but especially in general relativity, it's useful to calculate things that don't depend on who is looking at that, okay? So you want to calculate invariance, stuff that everybody's going to agree upon, and not just some observer because he's using some set of weird coordinates, okay? So it's really standard to use the Kretschmann scalar, this guy. So you contract into a scalar the Riemann tensor, okay? When you do that, then you'll find, and it's in the Mathematica, I think in the same Mathematica notebook, because it's so easy. Then you calculate this guy, and you find 48 m squared over r to the 6. So nothing weird at r equals 2m, something seriously wrong at r equals 0, okay? So gravity really is going berserk at the origin of your coordinates, okay? So we call this a space-time singularity, and you kind of could suspect something was going wrong, no? We're setting the field equations g mu nu equals to 0, so it's vacuum all the way, but you're demanding that something non-trivial when you're saying, well, I have some gravitational mass here, right? So all of the gravitational mass needs to be in a point because everything is vacuum, and if you do that, well, you get the same issues that you get in classical electrodynamics, if you wish, right? If you set the electron to be a point-like charge, then things are going to blow up at the location of the charge. So you need quantum physics. Now, to understand the 2m surface, you know, I'm doing this in 10 seconds, but of course, this took many, many years, okay? There's various things you can do. One of the things is really just try and change coordinates and see if there's a set of coordinates where things look just decent, okay? You can try this. I mean, these are not even the standard set of coordinates you could use for that, but you could try to change to capital T and capital X instead of small t and r, okay? So if you do this change of coordinates, you're going to find very quickly, it's a 1-minute exercise, that your line element looks like this, okay? Again, capital T and capital X. And there's nothing weird now about the r equals to m surface. It's a perfectly ordinary looking manifold. There's nothing strange about it, okay? So we conclude that there's some singularity at r equals 0, okay? But 2gm over c squared, if you wish, is perfectly okay. I'm going to call this the Schwarzschild radii, or the black hole horizon, okay? Now, the fact that there is a singularity in the interior of this 2m surface is actually a generic result, okay? It's a part of Penrose's singularity theorems that state that if you have, well, standard matter and you have an horizon somewhere in the space-time, okay, then there's no way around it. Something needs to go wrong in the interior of that horizon. Either matter becomes crazy, or space-time ends very abruptly, or the space-time even loses meaning, or you just really need quantum physics to understand everything, okay? Actually, this is the main point of my lecture today. This is why we should all think carefully about black hole physics. There must be something new there. okay? Because the the classical field equations don't make any sense, okay? Now, what does this mean? I have really no idea. I don't think anybody does. Does it mean that if there's a better theory than Einstein, it's going to percolate to the exterior of the horizon, and to which level? Now, that's up to observation, so that's up to you for the next decades to come with the answer, but this is really a strong motivation. Why, if there's new physics coming, they are coming from black holes? And I think it's also useful to say that we've been testing Newton's theory for centuries, and it's a beautifully tested theory in the weak field regime. So at scales of the solar system, Newton's, and of course the improved version, Einstein's theory, are tested, and they pass all the tests with flying colors, okay? But we're talking about tests where the gravitational potential, some measure of how strong gravity is of order 10 to the -6. You can just calculate, the gravitational potential at the surface of the sun or the Earth, 10 to -6. If you do the same for these objects, now you're talking about 10 to the 0, okay? So we're going 6 orders of magnitude. It's perfectly, I would say, legitimate that something new happens. Very good. Now, of course, the first thing that we did back in the 70s, when we started to understand exactly what we were looking at, I mean, the solution, the Schwarzschild solution, is around since 1916, okay, just to be clear. But when we started to understand what exactly we were talking about, then the first question is, well, it's so special. This is spherical symmetry in vacuum. So what happens in the real world? Am I still going to be left with this stuff or no? And it was very surprising when we started to study generic matter contents, okay? Let me give you one example. This is really just one example of the things you can do to try to understand how generic this space-time structure is, okay? So for example, instead of looking at vacuum, you look at a theory that has a new degree of freedom. So a scalar field, this is the kinetic term for your field, and then you allow some self-interaction term. For example, it could be a mass term. Really, it's just a name, okay? But anyway, something that goes like psi squared, psi to the cube, psi to the 4, whatever you want, okay? And we can try to see what happens when we solve the equations and look for something that looks like a black hole, okay?
What is K there?
Oh, K is 16 pi G. It's just the Newton's constant, just a normalization for Newton's constant, okay? That's a good question. I'm always free, I'm always free to change this K because it's going to give me exactly the same content. This is really just labeling Newton's constant here, okay? Is this clear? Okay, so I'm going to look for spherically symmetric solutions again, static solutions. You just plug this in the Mathematica notebook. That's the beauty of it. Just shift enter and there you go. Of course, now you don't have G mu nu equals 0. You have some stress tensor that comes from varying this action with respect to the metric, but it's more or less standard. The equations are there in the notebook, okay? So you look for a space-time that has a time-time component that I'm going to call F, some RR component that I call G, and the field equations that you actually can focus on are simply the Klein-Gordon equation, the stuff that you get when you vary this with respect to the scalar field. Okay, you need to extremize the action, so do it with respect to the scalar, and you're going to get this equation, okay? Yeah. Oh yeah, you can do that. So you can change. So this is a beautiful question. We could also change this theory and put here, I don't know, psi or some function z of psi directly coupled to this Ricci scalar. What is this going to give you? Actually, this ties with the previous question, right? Because k is Newton's constant. So if you actually multiply the Ricci scalar by some function of the field, it tells you that Newton's constant is varying in the spacetime, right? So if you have a non-trivial degree of freedom, non-trivial scalar, then the Newton's constant is varying as you move along in spacetime. You can do this. And the outcome is exactly the same as what I'm going to say. Because there's a nice change of coordinates that takes that theory. So when we multiply this guy by some function of the field, there's some there's a nice change of coordinates and the scalar field that rewrites this in this form. Yeah. Okay. Now, if you look at the Klein-Gordon equation, it looks like this. Again, it's second order. It should be second order. Psi is time independent. Okay. Hence, you don't see any derivatives with respect to phi, but you do see prime is a derivative with respect to r. Okay. You should check this anyway. I mean, don't believe what I'm saying. But you see, I'm not using the full set of Einstein equations. I'm just really just looking at the Klein-Gordon equation. And I'm going to assume, and I'm going to comment on what this means, or at least why I'm doing this. I'm going to assume that there's a value, psi 0, that minimizes the potential V. Okay? For example, if you have a mass term, if your scalar is really just a massive guy, then V is psi squared times something, times the mass of the field, okay, or times half the square of the mass of the field, whatever, okay. But in that case, then psi 0 is 0, okay.
Are you imposing that psi is not depending on time, or is it a result that?
No. I'm imposing that psi does not depend on time. Yeah. Well, so you can also show that in spherical symmetry, if psi depends on time, exactly the same thing holds. I haven't told you what that thing is, okay? But anyway, the same outcome. But there's interesting developments that I think I will go through on lecture 3. Okay, so now what I'm going to do is I rewrite this equation over here, okay, in this form. The only thing you do is you multiply by r squared psi minus this minimal guy, psi 0, okay? So nothing out of the ordinary. And I'm going to assume, because I am looking for black hole solutions, I'm going to assume there's an horizon in the spacetime, and the horizon corresponds to a 0 of this guy here, G. Think about the Schwarzschild solution, okay? The 0 of this guy of 1 over GRR gives you the location of the horizon. So I'm going to do the same. And then, if there is a 0 at r equals the horizon radius, okay, a 0 of G, I integrate this equation here on the left and the right-hand side from RH to infinity, so across the black hole exterior. And what you get is this, okay? Of course, you need to do, so you need to rewrite, so you're going to integrate this guy, okay, integrate by parts, so you get a total derivative, and then you push the other term to the right-hand side, this guy, okay? So you're left with something that looks like this. It's not terribly complicated, okay? But by definition, if there's an horizon G, that function G at the horizon has to be 0, okay? By definition. Therefore, look at this. This guy is really just a boundary term, okay? So if you're looking for something that's beautiful, meaning regular, finite everywhere, smooth everywhere, then at the boundaries, this guy is 0 because nothing is blowing up. So 0 on the left-hand side, okay? Now we need to look at the right-hand side. But if there is a single minimum, so if this guy has a single minimum, well, this guy is positive, and this guy is also positive. Remember, my definition of psi 0 was the minimum of that field, okay? So you see, it's a very simple proof. It's called a uniqueness result to show that if you start adding matter, granted, it's a very special type of matter. It's really just a scalar degree of freedom. But you can't do much. It seems that the field equations force you to vacuum, right? So the upshot of this is, if you want to look for a regular spacetime, a regular black hole spacetime, when you add a scalar degree of freedom, you're still stuck with Schwarzschild. It's amazing. Okay, it's spherical symmetry, but still. Sometimes it's common to refer to this as the no-hair property. This is not really a no-hair property. It's a uniqueness result, because we're really looking at the full set of field equations. Tomorrow, I'm going to show you what a no-hair property looks like. No-hair means you start with something, you try to look at deviations of that something to see if hair, well, I have lots of it, if hair is possible, okay? And you're going to see that if you're looking for new solutions on the vicinity of something that you know, then you can't get them. Here, we're looking at a very general scheme, okay? Very good. Now, this is for spherical symmetry. You can do this, you should do this in full generality. I am not going to do this, but the result is the following. If you look at G mu equals 0, and you look for an asymptotically flat, meaning our universe, okay? Something that's nice and goes to Minkowski at large distances, there is only one family of solutions that's called the Kerr family of solutions, the Kerr geometry, okay? I'm going to show you the geometry. And it has only two parameters, mass and charge, okay? And this is the second, I could be done now, I would have done my job, okay? Black holes are amazing because things go badly wrong in their interior. And black holes are amazing because they're so simple. I mean, two parameters, mass and spin, suffice to characterize any of the trillion of black holes out there. Just look at me. If you want to specify who I am, think about the 10 to the n parameters you need. Oh, well, he's 2 meters high. 75 kilograms. He has, I don't know, 10 to the 7 number of hairs in his body. His eyes are whatever. You see? Black holes in Einstein's theory take two parameters. I think it's never too much to tell this to your family. I'm studying black holes. These guys are incredible. So they're simple. And the reason why we should care about this is that when you start trying to test the gravitational interaction, you know, you'll come across a lot of dirtiness. I mean, especially if you're doing astrophysics, all the systematic stuff that you have there, it's amazing. But with black holes, most of that stuff is absent. So they're beautiful tools, beautiful laboratories, and there's another piece of thing that makes them really special, and I'm going to go through that next. That relates, of course, to the fact that they're able to empty themselves of matter when you get to really strong, to really the strong field regime. Okay, so let's look a bit at the motion of matter in black hole geometries. Now, motion in general relativity, the problem of motion, the two-body problem in GR, it's amazingly complex, okay? People have been working on this for, well, since the theory was devised. It's not an open, it's not a closed problem. You know, there's all sorts of tools that you can use. You can use a post-Newtonian expansion where you're far away from sources. You can use a post-Minkowskian expansion. You can use all sorts of things. There's a lot of groups in the world trying to look at this. However, if you're satisfied with looking at the motion of very light objects in the motion in the vicinity of a black hole, then we know what to do. Okay, roughly. We know what to do because this guy really is not altering this. So you have a small thing like myself, and you throw me close to a black hole. I'm not really going to disturb space-time very much, okay? And so this is an easy way to start. Let's look at a point like test particle and see what it does, and then maybe we can use that as a starting point to get the corrections. I'm not going to do the corrections, I don't think, but you can use the 0 point, okay? Now in the 0 point, you just take the extension of the results that you had in special relativity. So you start with a Lagrangian, which is written down here, okay? And then, well, motion of particles is, if it's a null particle, if it's like a photon or a high frequency graviton, this guy is 0, it's the line element is 0. You travel on a null cone. If it's a time-like particle, then the normalization is -1. This is more or less a standard extension of special relativity. I think it looks, when you do this, that there's some jump in the properties of matter versus photons. There isn't, okay? There's a smooth transition between time-like motion and null motion, and I think we're going to see that in a few seconds. These equations are actually equivalent to the geodesic equation, which is written down here. Again, a second-order differential equation that you can just integrate. I don't have a notebook here because there's a nice effort going on for the last 2 years called the black hole perturbation theory that has nice integrators of the geodesic equation. It also, motion of course is embedded in the field equations. So if you take the stress tensor for a point-like particle, okay, and you use the Bianchi identities on the Einstein equation, so you know Jimmy knew the Bianchi identities for this are 0. So if you do the divergence of this guy to 0, then you get exactly this equation. Okay? So Einstein knew what he was doing. Very good. Now let's try to look at what happens in a black hole spacetime. So I'm going to do spherical symmetry, okay? Staticity, no time dependence, and if you look at the metric, no azimuthal dependence, phi was absent, right? So that gives you two conserved quantities if you look at the Euler-Lagrange equation, right? ddt, well, I don't remember them. I do. Okay, so the two conserved quantities are time translations give you an energy, conservation of energy, okay? Some energy parameter, E, and then you should go to large distances to relate to Minkowski quantities. And then azimuthal symmetry, some angular momentum parameter. Okay? So what you get is there's a conserved guy which is F. F is here. 1 minus 2 gm over c squared r. And angular momentum r squared. By the way, dots here are derivatives with respect to proper time. Okay? And this guy over here gives you the normalization, right? So when you do this, it's really a half-a-minute exercise. So we have everything. We have two conserved parameters and then an equation to get how particles move, right? So we have an equation for r, an equation for phi, and that's all we need. Because of symmetry, we don't need to worry with theta. We just fix a plane and that's it, okay? So let's do that. The first thing you can try to do is, well, let's look for circular motion, right? Because that's just easy. There's a reason for that. But let's look for circular motion. Then you want r dot to be 0, r constant, r dot to be 0, okay? And you're stuck with this. So let's look at time-like. V prime, so the conditions, let me go back. Remember, when you think about r dot or r double dot, this is v or v prime. Taking the derivative with respect to proper time really is the same as taking it with respect to r and multiplying by r dot. So v dot or v prime is going to be the same. Okay, is this clear? And of course, again, circular means r dot 0 and r double dot 0. You don't want the particle to be doing this and then falling. You want it to be doing this. Okay? Good? There you go. So V prime 0 gives you a relation between angular momentum and energy. Think about centrifugal force and gravitational force. That's the equation. And V0 gives you an extra condition. And it's nice, okay? It tells you immediately that there is no circular motion when R is smaller than 3m, right? Because energy needs to be positive. You can look at syntonic locations far away from the black hole. E is positive, okay? So nothing, so we call this surface the light ring or the photon sphere. There's no circular motion within the surface 3m. And it's going to play really an important role in all the things I'm going to say in these lectures, okay? I'm not going to do the calculation, but you can actually show that time-like matter can only be on stable motion if R is larger than 6m. Okay? We call this the innermost stable circular orbit. And it's fine. So it tells you already, geez, I'm going very slow. So I'm going to run now. So it tells you immediately how you can look for black holes. You just look for regions where you have matter around it and they are truncated at some point close to this distance. If you find a region which is bright and then has a dark spot, that's a good bet to look for a black hole. Okay? Let's look now at, so there's no stable motion within 6m. If you do null particles, so delta 1 equals 0, the normalization, remember it's null, then there's only one solution to this. R equals 3m is the only possibility. And it's nice, it connects smoothly to the time-like properties, you see? So matter can orbit on circular trajectories all the way down to 3m, except that the energy per unit rest mass diverges at 3m. There's your null, your light ring, okay? And everything between 3m and 6m is unstable. So of course, light orbiting on this light ring cannot be on a stable motion. It's unstable. Let's calculate the time scale, okay? Well, you just use the equation of motion, you fluctuate it, so you assume you have a photon which is at 3m, so this RC, plus some delta. You kick the photon a little bit, okay? And you see what happens. You expand the equation of motion, and you find that the solution is this small delta. If you kick a bit the photon, the separation away from the light ring is going to grow exponentially on this rate, okay? It's a super important number that anybody that reads Chandrasekhar knows by heart. So I hope at the end of this lecture you know this by heart. Because this is the time scale of LIGO as well, okay? So if you throw photons, if you shine this laser beam close to a black hole, it can orbit on a circular motion, but on time scales, let me push this. Remember m expressed in seconds, okay? On time scales of 1.5 milliseconds for a 30 solar mass black hole, that was the first LIGO event, this photon is going to just go away from this light ring, okay? I'm talking about photons, but you can do exactly the same for high-frequency gravitational waves. They also are able to orbit a black hole, but they need to decay. And they decay on these time scales. This is exactly the last stage, I'm going there tomorrow, the last stage of what we have been seeing in the LIGO signals. Okay? Very good. I still have 10 minutes. So let me summarize. I haven't said half of what I wanted, but it's fine. Now, let me summarize this very quickly. So if you do an equatorial slice of a black hole spacetime and you start throwing things there, you will see that at large distances, matter can orbit on a stable motion. Of course, you need to recover Newtonian physics. But as you go inwards, then you'll see, well, there's no matter within this 6m orbit because motion is unstable. It just falls onto the black hole. This area should be totally depleted. Okay? And whenever there's some dynamics going on with the black hole, this dynamics is dependent upon this light ring thing. this photon sphere. In fact, all of the if you throw a star onto a black hole, okay, if you throw a star, you will see the star approaching the black hole. It's fading because of redshift effects. You know, the photons have to climb the gravitational potential. And at very late times, you're not seeing the star. You're seeing light that was stuck into the photon sphere, and it's slowly leaking out. That's what you're seeing. So the observational appearance of black holes is dictated by the light ring and never by the horizon. We never have access to horizon physics, ever. Good? Now, what about scattering? How do black holes behave when we start throwing things? I was just looking at circular motion. What happens if I throw photons? I shine, oops. Oh, this works. So I shine light on black holes. What happens? I shine this laser beam onto a black hole. Crap. Okay. What happens to this guy? What's the maximum impact parameter that it can have and still be absorbed by the black hole? The calculation is always along the same lines, right? So we have the equation of motion. I'm going to define an impact parameter, which is angular momentum over the energy. If you do the calculation, it's exactly how you would define an impact parameter. And the equation of motion gives you this. Gives you that, just look at r dot squared equals v. You get this guy, okay? Now, at large r, so when this guy goes to infinity, it tells you that there must be a turning point at sufficiently large angular momentum, at sufficiently large impact parameter. So if I throw a photon with a sufficiently large impact parameter, okay, it must have a turning point. This is the first conclusion, okay? It must have a turning point at large v. Now let's calculate the critical impact parameter. So I re-express, so I define a quantity y, which is r over, which is r over 2m, okay, over here. And I rewrite the equation of motion, r dot square equals v. You get this equation over here, okay? This guy is positive, so we don't need to worry about it. Remember, I'm trying to understand when this changes sign. I'm trying to understand if I throw a photon, when exactly the motion changes from outward to inwards, right? I'm trying to see if there's a turning point in the motion, okay? Now, if you look at the discriminant of this guy over here, you'll realize it's this number. So for impact parameters b smaller than, look at the magic number again, 3 square root of 3m, light falls onto a black hole. So it means if you start throwing photons in all directions to a black hole, there is a sphere of radius 3 square root of 3m, within which of each, all of the photons will be absorbed by the black hole. This is the absorption cross-section of black holes, okay? Photons with impact parameter larger than this go to infinity, no turning point. Smaller than this guy, they just hit the black hole. So they have a cross-section which is 27 pi m squared. There you go. This is exactly the type of physics that the Event Horizon Telescope is doing, okay? So, of course, we were looking at, is it okay? We were looking at photons which are emitted from faraway regions, okay? Now you should consider what happens in general. If I have, I don't know, matter orbiting the black hole and a star, now you need to do this but for a photon that's emitted close to the black hole. The idea is always the same. The integration is exactly what we've been doing. There's no new magic here, okay? Of course, you can have interesting features. For example, this guy. Take a star at this point, okay, and a spinning black hole. Then you can have photons that reach an observer here, taking very different paths, right? You can have a photon that does this. It goes behind the black hole, gets lensed by the black hole, and hits the observer. Or you can have a photon that does this. Goes once and a half around the black hole and then hits the observer. Okay? Extreme lensing. So in fact, if you look at this guy, this would be the green photon and the blue photon. It seems that it comes from different regions on the sky, but it actually came from the same source. Okay? That's what the Event Horizon Telescope is doing to get evidence that there's light rings in space-time. Okay, we just started, but I think it's a very interesting effort. And in my next 5 minutes, I will try to add rotation and tell you the new things that arise. Okay? Are there questions? Good. Now, when you add rotation, yeah.
Tell me again, what is the absorption cross fraction? Because I see that is 27 pm squared. That what are the units or what is that? Is a radius or what's that?
Oh, yeah, it's an area. So, yeah. So this number should be multiplied by g squared over c to the 4. Okay? It's a radius squared. Cross section is always area. But if you think about it, it tells you that all the photons that come within a radius 3 square root of 3, there's a flat circle here, they all get absorbed. Okay? The critical, this is a good question. The critical, so let me try to draw here. I have my horizon here. Okay? I have my photon sphere. Can you see this? Here. I see disaster coming. Okay, can you see this? This is the photon sphere. This was at 3m. Okay? What this means is the following. If you throw a photon with a very large impact parameter, it's going to go and hit infinity. Okay? The critical photon is a guy that comes here with 3 square root of 3m. What does this guy do? Well, this photon, this critical guy, does this. It circles an infinite number of times around the light ring. So thank you for the question. So the critical photon to be absorbed, it's shot with an impact parameter of 3 square root of 3 and circles the black hole an infinite number of times around the photon sphere.
Another question is the photon sphere is related to the structure radius, and this is the same because I remember that is a correlation between 1.5.
Oh, yeah. Yeah, the radius of the light ring, well, you don't see it, but it's 3 gm over c squared, which is 1.5 the horizon radius. Yeah. Because the horizon radius is 2m, okay? Everything? Good. Now, when you add rotation, you need to believe me, but you can check with Mathematica notebook that this solves the field equations, okay? This is the general vacuum solution of the field equations. There's the two promised parameters, which is the mass m, where is the mass m, and a parameter that's related to the angular momentum, the parameter a. Actually, the angular momentum of your black hole, if you plug c and Newton's constant there, is something like this. You will also realize that if you want to have an horizon there, then this guy, this delta, has to have real roots. Okay? And for that to happen, then A, I'm not going to sign this, A over m needs to be smaller or equal than 1. So if you want to have a black hole in the space-time, it needs to spin slowly. Well, according to this measure. But by the way, it's always important to realize that the number on the left is of the order 1 for the Sun. If you calculate this number for the Earth, the planet Earth, is of order 10 to the cube. If you calculate this number for a spinning top, something that we would play as a child, This is of order 10 to 17. Okay? So black holes spin very slowly, according to this measure at least. And I'm going to try to use this, but not today, to destroy black holes. Okay? But anyway, let me finish. I see 1 minute. Let me finish with the following. A very simple, trivial calculation. You have this space-time, and we're going to assume to take a time-like observer, like myself, okay, and place this observer with a powerful spaceship in this space-time. The spaceship is so powerful that myself, I'm in that spaceship, I'm at rest in that coordinate system, okay? I'm at a fixed r, theta, and phi. Well, then, here you go. This is my 4 velocity. I have the space-time, so I can calculate the covariant guy. It's GTT times VT. It's my only component. So when you square this guy, you get that V squared, okay, is GTT VT squared. Now, this guy is positive, okay? Right? For Schwarzschild, GTT is negative. It's minus 1 minus 2m over r. But for Kerr, if you look at this, for Kerr, this guy, GTT, can become positive, okay? Now, if GTT, if you're placing this spaceship in a region where GTT is larger than 0, then I cannot remain at rest. This region has a name. It's called the Ergo Region, okay? And it means, really, we are forced to co-rotate with the black hole. Some people call this frame dragging. It means we really need to go along with the flow. And before Jorge kills me, let me tell you how we can use this to extract energy away from black holes, okay? So I do this device. This was done by Penrose. It was different. This is really just my version of it. You take a spinning black hole, and you build something with metal, with iron, okay? There you go. You have this metal bar attached to a ring that you place inside the Ergo region. Because this is inside the Ergo region, it can't remain at rest. It needs to spin with a black hole, right? Well, but this guy is attached to some magnet, so the magnet needs to rotate, no? But now I put some coils. It looks like a very complicated, huh? I put some coils. Faraday induction law tells you there's a varying magnetic field, there's a flux, so I'm going to light this bulb up. Of course, energy has to come from somewhere. It came from the rotational energy of the black hole. It's a beautiful example. Actually, in the original book, Penrose was not using this construction. He was using just garbage. An alien civilization could use garbage to generate energy out of spinning black holes. This is not super weird. We could do this for a star. No, you just anchor this mechanism in a star or in a carousel, whatever. I mean, I'm doing this. I can extract energy. But you see the magic of this process. The magic of this process is that you're doing this in vacuum. It's unbelievable. I mean, there's nothing there that supports this guy. It's vacuum. The guy is forcing to co-rotate in emptiness. You see what I mean? It's amazing. So, okay, I will stop here. Thank you.
Comments?
Hi, thank you for the nice talk. So I have heard this statement that time and space are interchanged inside the black hole. So can you explain?
That what?
Time and change interchange their places inside the black hole.
Diamonds.
Time and space, yeah, swap inside black hole.
Oh, time and space. Oh,
Space,
yeah, of course.
So
That's, well, of course, that's more or less. Let me. You see, I think in general relativity, it's always good to keep in mind that these are just coordinates, just names. Just because I call this T time, it doesn't mean it's a time coordinate. It doesn't mean it's something you measure on the watch. Okay? And if you think about Minkowski, indeed it isn't when you're in the black hole interior. Because you see, it changes sign. In the black hole interior, T and R exchange roles. You see, R becomes time-like and T becomes space-like. So this is not a good set of coordinates to think about what happens in black hole interiors.
Okay.
Right?
Okay. Thank you so much.
Thank you for the talk. Maybe it's a silly question, but when you speak about the mass, where is the mass in a black hole? Because when you have a compact object, you have a density profile, and the mass is times the volume.
Yeah,
but
yeah.
here,
It's here. It's at R equals 0.
yeah, but where is in is in the
That's $1 million question, no? That's $1 million question. So what the theory tells us is that we can kill a star. We've seen this. We do numerics with this, okay? We can kill a star. We can end the fuel. We see the star collapsing, but we have no way, actually, of even doing the evolution in the black hole interior. So where, in the end, is that matter going to end up? We have no idea. In this nice and simple solution, it's at a point. But this cannot be the final answer. Quantum effects, for example, need to at some point prevent the collapse to be eternal. But this is the best answer we have at this point. Does this answer your question?
more or less? Yeah, thank you.
I think this is not too dissimilar from what you get in classical electrodynamics, okay, where the electron is point-like. When you start doing quantum physics, it's smeared, right? You get vacuum polarization effects. I'm sure we're going to get the same here. To what extent this changes the exterior, I have no idea. I don't think anybody does.
I'm almost sure this is a stupid question, but when you derive the 3 over square root 3m cross section, let's put it this way, you introduced the concept of angular momentum, and so I thought that the question was general to spinning black holes as well. But then you introduce curve metric, etc. So
Oh, no. This is angular momentum of the particle that you're throwing in. This guy is at rest, is not spinning.
but
Okay.
then you add the so in the definition of B you add L over m.
But
or
this
over
L,
E.
but this L is the angular momentum of the
particle.
particle that you're
Alright.
throwing in.
All right. So this equation changes if you have spinning black holes, etc.
Indeed, I was supposed to show it today. I will show it tomorrow.
So just to be sure I understand. Also, when you define the angular momentum with the phi dot, etc., this was all for the particles, not the black hole.
All for the
The
particle.
black hole is in
All for the.
All right.
What you will see is that when the black hole is spinning, you either have addition effects or
Yeah,
subtraction.
exactly. Okay, thank you very much.
Okay, one last question.
Hi. Just a question about the last slide. So, if you extract energy from the black hole, does it mean that the spin of the black hole decreases?
Yeah.
But so it's not anymore static, right?
This is not a curved black hole is not static. It's stationary.
Okay.
Okay.
Right. Thanks.
Okay, thank you very much, Peter, again. Let's welcome our second speaker, Francesca Calore, who is going to talk about cosmics and gammas and everything.
now is it working better? Okay, good. Okay, so first of all, I'm very happy to be here. This great school. I looked at the program, sounds amazing. And I'll be asked to introduce you a bit about how we can probe fundamental physics with cosmic and gamma rays. And of course, the first part of my lecture will be then devoted to really look at those messengers from the high energy universe, so basically the first hour of today. Charged cosmic ray, gamma rays, and neutrinos, in order to understand how those are produced in the more standard scenario of standard, boring astrophysics, how we can detect them, and how we can actually have them going from the source up to us. And I would then frame my title here for this first lecture in what we can really do to probe fundamental astrophysics with those messengers, because besides new physics, which will be the topic of my later lectures, we can also do very much about astrophysics and how to learn properties of cosmic ray accelerators and also properties of these very same high energy particles. So let me go through a list. So here is a list of few references that I leave you for further notes. And I really invite you to follow the lectures, the public talks by Malcolm, because he's great, one of the founders of very high energy astrophysics. So let's start with putting everyone on the same page, since I don't know how many of you are more astro or how many of you are more particle. So the main environments that we will deal with are either within galaxies or in extragalactic environments. So galaxies and the extragalactic space, they are characterized by being very, let's say, not very dense environments with, in terms of matter, but they may be very magnetized environment with strong magnetic fields. Typically, they have a very large distances of the order of kiloparsecs in the galaxies, and of the order of even gigayears or megaparsec in the cosmos, and very long time scales that we can probe with those different particles. So just to remind you that when we talk of parsecs, which is about 10 to the 16 meters, so our galaxy is about 20 kiloparsecs wide in terms of its light content, but it might be much larger if we consider the dark matter halo. The magnetic fields that we are looking at are of the order of microgauss in galaxies, and in extragalactic space might even reach nanogauss, although it's a bit much more difficult to set upper limits on those magnetic fields. You will see often these system of coordinates where you have the galactic center and the sun position here, which are typically at 8.5 kiloparsec away. This number can vary a bit, but it's measured with good precision. And you have the longitude coordinate running along the disk, and the latitude that describes the angle between your object, for example, a star here, and the galactic plane. So some facts from the Milky Way. It's made, of course, of a lot of stars. About 10 to the 10 solar masses are in stars in the galaxy. You have also a lot of gas, about 10% of the mass of the Milky Way, for a total mass of around 10 to the 12 solar masses. This also is a number which is not measured with, let's say, particle physics precision. It can run from 5 in 10 to the 11 to 5 in 10 to the 12, depending on the tracers for the dynamical mass of the Milky Way that you use. And as I said, you have the radius of the Milky Way, which is, let's say, the light part of the stars is about 15 to 20 kiloparsec. And if you consider the much larger halo of dark matter surrounding the disks of galaxies, or the bulge of galaxies, then you have a much larger halo of about 300 kiloparsecs. So what do we know about cosmic rays and how do we measure that? The story of cosmic rays dates back in the early 20th century with the discovery of cosmic ray by Hess, which then got the Nobel Prize in 1936. From there, there was a quite broad activity of trying to build extensive X showers on Earth in order to try to detect those particles for the cosmos, but also trying to go up at higher altitudes in order to reduce the contamination and really get the primary particles impinging the atmosphere. So first with balloons and later on with instruments, so detectors, built on the ground and then sent to the space on satellites. And this is an example of AMS, so the alpha magnetometer spectrometer here, and on board of the International Space Station. So we had a large discovery of particles that then kind of matched also an effort which was parallel to that in Astroparticle, which was the particle physics development with ground-based machines and the discovery of heavy elements. So today we are in the realm of really multi-messenger astrophysics. So we used particles, we use photons at different wavelengths from radio up to very high energy gamma rays, but we also have neutrinos and very recently gravitational waves, which is bringing a whole new plethora of information in this domain. And finally, we would like to discover some antimatter in cosmic rays, but this is not the case yet. So let's have a look at the cosmic ray flux. This is the typical plot that you might have seen many times. It was the Wikipedia plot here. But this is the flux as a function of energy. And you see the first really striking thing. You have cosmic ray, this cosmic ray spectrum. So this is the all particle spectrum without distinction of flavor that runs over more than 13 decades in energy and about 30 in flux. So the flux is just the number of particles per unit area, per unit steradian time, and you might have the differential flux in energy as in this case. So you also have 1 over GV or whatever you are using for your energy. It is incredibly like a smooth spectrum without many features. So you see it's almost a pure power law with an index of about -3. And it has a few features, which in this scale here you cannot see very much, but there is a feature at about 10 to the 13th, 10 to the 15th, sorry, EV, which is called Gni. And then you have another one at 10 to the 19, which is the Enkel. So these are better seen if you were to multiply this by e to the -3 or e to the -0.7. But the point is that these different points, there seems to be a change in this power law, in this index of this power law, which people have started to investigate. Is that connected with really some deep behavior of cosmic rays and accelerators? So really, what is the origin of those different cosmic rays, and why here you have this change of slope? It's also a rather isotropic distribution. So for example, now we try to measure the anisotropies of very high energy cosmic rays, and this is consistent with an isotropic distribution of sources within tens of %. But really, how do we measure them? So the measurements of cosmic ray can be done in 2 ways. One is what we call direct detection. If the cosmic rays are below a few tens of TeV, then we can measure them directly in space, because they can leave a trace either in balloons or on detectors on satellites. And this is also because the cosmic rays are absorbed in the upper part of the atmosphere, so it cannot really go through down to the ground. So those direct measurements can exploit, for example, magnetic spectrometers that are on satellites, which allow to distinguish the charge. This is the case of AMS. or calorimeters, like, for example, the Fermi satellite that we will see in the follow, that actually have the possibility to measure the full energy of the particle, but they cannot distinguish the charge. At higher energy, what it occurs is that you have, first of all, a limitation in the energy that the calorimeters or detectors on satellites can detect, because of course you will need to build a very large detectors in space, and this is not feasible. And also, so that you have very reduced statistics on space. But those energy, what occurs is that the atmosphere works as a huge calorimeter, so is not opaque any longer. So cosmic rays of very high energy can penetrate the atmosphere, can induce showers in the atmosphere, and then they can leave the trace of this shower on the camera of, let's say, for example, optical or water Cherenkov telescope. So this is called the indirect measurements, and we have a plethora of instruments deployed on Earth. We have imaging Cherenkov telescopes to measure energies up to the TeV, so photons up to the TeV, like, for example, MAGIC, HESS, and Veritas. Then we have water Cherenkov tanks, like HAWK, that exploit the Cherenkov light, which is induced on the water tank and can measure very high energy particles. But then we also have, for example, fluorescence detector, and other type of techniques to detect indirectly this kind of particles. So just a bit to tell you how the development of the shower works. There is a difference between cosmic photons that impinge the atmosphere and then develop an electromagnetic shower with respect to if you have rather a proton which impinge the atmosphere. So if you have gamma rays or electrons, you have an electromagnetic shower, which is pretty easy because it's only the cascade of the photons into electron-positron pairs triggered by the layers of the atmosphere. And so there are ways to try to understand the development of the shower in a semi-analytical way. This was a very simple model, the Heitler model, and everything boils down in measuring what is the grammage, which is the characteristic length over which you have the production of a pair. And you can relate this grammage to the number of pair conversions that you have in the atmosphere, and derive that on average the photon should have should be related to the energy of the initial photon divided by 2 times the number of conversions that you have. And there is a maximal energy above which the conversion is not any longer efficient, which is about 80 MeV. And so you can also have a maximum of the development of the shower in these vertical coordinates here. So you really know how to model the shower and how to, from the image of the shower, basically to reconnect to the initial energy of the impinging photons, which is the thing that you want to measure. So for every photons that comes from the cosmos, you look at the shower, how the shower developed, and leave the trace in the camera, and then you can go back to the energy of the impinging photons. And this is the quantity that you need to know. For hadronic shower, the development of the shower is more complex because you have, for example, a proton, which then develops an hadronic cascade in the atmosphere. It's a very much broader shower on Earth, so it's of the order of kilometers. This was of the order of few meters. So you really need arrays of detectors that can then put together the images to reconstruct the full shower. And you, of course, go through the production mainly of pions, so charged pions and neutral pions that leads to photons that then convert to pair. So there is also part of electromagnetic shower in the hadronic. And indeed, you can measure, you can relate the average energy in the hadronic part of the shower and the electromagnetic part of the shower, again, with the main energy of the impinging particle. So by measuring the hadronic energy and the electromagnetic energy of the shower that developed, you can then go back to what was the energy of the impinging protons, and this is what you really need to know. Finally, I also would like to mention neutrinos, although I won't go into much details, but neutrinos are detected to optical Cherenkov telescopes in very clean environments, like ice on water. So this is an example for ice cube in the South Pole, where you have about 100 strings of photomultipliers that are within ice and allows you to measure the tracks that neutrino leaves when they convert into muons, basically. So the idea is that you want to reject the neutrinos that are produced by, for example, protons impinging the Earth. So you don't want to retain as your cosmic neutrino flux the neutrinos that comes from conversion of cosmic rays in the atmosphere, as I shown before. Of course, you also produce neutrinos in those interactions, but you only want to keep really the cosmic neutrinos that are the neutrinos that are produced originally from sources in the outer space. So you in order to be able to reject most of the cosmic ray neutrinos, what you look for are tracks that comes from the innermost part of the detector, so from down deep Earth, exiting the ground. So those tracks are then retained, and then there are betas applied in order to identify the cosmic neutrinos. So there is also a new idea that I want to mention. This is the Grand Telescope. It's a giant radio array that would be able to look for coherent radio emission of air showers that are produced by tau neutrinos that are skimming the Earth, really are very horizontal showers, and can lead you information on the original cosmic ray neutrino flux. All those particles that I mentioned, charged cosmic rays and photons, they do have an horizon. So we cannot detect photons and cosmic rays from wherever in the universe, but there is a limited horizon from where they come from. And in particular, if we consider protons, what it can occur is that they interact with the photons of the CMB. And this proton CMB photon interaction produce protons and pi zero. This is a reaction that has a threshold, so it can occur only if you have a given energy of the proton, which depends on the field of the energy of the CMB. So you see that for typical values of the CMB energy photon, you have a natural limit of 10 to the 19 electron volts. So it means that you do expect a cutoff of the charged cosmic ray spectrum at about 10 to the 19, and this is the so-called Grisen-Zechtin-Kuzmin cutoff, so the GZK cutoff. You don't expect heavy particles to come, let's say, charged particles to come from farther away, because of these really fundamental limits, which set also a limit on the distance. So you can see the horizon of your charged cosmic rays or protons is about 50 megaparsecs. And the same is for photons. So photons also, they do interact with the environment, and in particular you can have a photon which is emitted from an high energy source that encounter the photons of a field which is the extragalactic background light. This is the field of photons, the radiation field of photons that is permeating the universe, that comes from the emission of the galaxies in the outer space. So whenever you have a high energy photons encountering an ABL photon, that you can produce pairs, so electron and positrons. This is again a reaction that has a threshold in order to produce electron-positron pairs, and you can work out what is the horizon. But the main point is again that for photons you have the intrinsic flux which is emitted by a source. let's say a power law, is then modified by the fact that photons has to travel the outer space and encounter these ABL photons, and so there is this this process of absorption. So the spectrum of high energy sources in the deepest galactic space is not does not correspond to the intrinsic spectrum, but is typically absorbed. And you can recast this absorption in an optical depth, which relates then the intrinsic emitted flux with the observed flux. So if we look at the different horizons for different particles, this is the distance in megaparsec as a function of energy. So you see that the universe is mostly transparent to all particles if we consider galactic distances, so for example from the galactic center to us. But if we want to start to probe far galaxies, starting from the nearest one down to cosmological scales, then you see that starting from 10 to the 12 electron volts, you are starts to be opaque to this kind of distances with photons. So you need to rely on neutrinos and gravitational waves if you want to probe this part of your space with astroparticle physics. So let's go a bit more in details of the charged cosmic rays, and I want to give you a few highlights about how cosmic rays are produced and how are they transported, mainly within galactic environments. So a bit of recap about how does a charged particle moves in a magnetic field, because this is what occurs, for example, in our own galaxy, where there is a magnetic field of the order of microgauss, as mentioned before. So whenever you have a particle with charged particles, it feels the presence of the magnetic field. And if you consider the magnetic field line direction, you can solve the equation of motions for these particles, so how the momentum changes with time. And you can recover the equation of motions, which in a constant magnetic field and in the absence of any additional electric field leads you to a constant momentum in the z direction, if the z is the same direction of the magnetic field, and velocities that change in the x-y plane. So you have this licoidal structure of the direct tracks of the charged particle. And you have two typical quantities which are important to remember. One is the Larmor radius, so how large is basically this trajectory, and which is related directly to the intensity of the magnetic field and also the rigidity, so the, say, energy of the particle. The rigidity is nothing else than the momentum divided by the charge of the particle. And you have also the Larmor frequency, which again depends on the charge, on the magnetic field, and on the energy of the particle. And the two quantities that are sufficient to describe this motion. So, but what happens if instead of having a constant magnetic field, an homogeneous one, you have small perturbations on top of it? And this is indeed the case in our own galaxy, where you can measure the power spectrum of the fluctuations of the magnetic field around a mean average density. So if those perturbations are small, so are really at small scales, what we can add is this fluctuation term here, and we can expand around that, and we can see that y, as mentioned before, the constant part of the magnetic field only changes at y and z and y and x component of the momentum. For the fluctuations, as long as they are small, they do change the direction of the z component of the momentum of the particle around the magnetic field lines. However, if you average over mu in time, the average of this is still 0, while the variance is changing. And those are typical characteristics of a process which is purely diffusive. So we have a diffusive propagation of cosmic rays in the presence of stochastic fluctuations of the magnetic field. And how does the particle diffuse? So this is a collision-less diffusion because basically it scatters off the inhomogeneities of the magnetic field. And how the particle trajectory is affected depends on how the wavelength of those perturbations compare with the Larmor radius. So if you have that the perturbations are much larger of the magnetic field are much larger than the Larmor's radius, well, the particle didn't really feel the fluctuation, so it just goes straight on doing his helicoidal movement around the magnetic field lines. The same, of course, occur if you instead have very small scale fluctuations of the magnetic field. It's much smaller than the Larmor radius. In this case, the particle just keep on doing his helicoidal movement around the main magnetic field line and doesn't feel the perturbations. But if the scales are comparable, then you have a deflection of the particle, so this change in pz becomes effective, and you have this diffusion process taking place. So the diffusion process is described by what is called the diffusion coefficient in momentum space, which describe how the momentum change in space with the perturbations of the magnetic field. And you can also, often you will see also some diffusion coefficient in energy space. And this is the main quantity that can be probed directly with cosmic ray measurement, but it can be then linked down to really the momentum variation.
Can I ask?
Yeah.
So to understand the direction where the ray came from, in situation 2 and 3, it's going to be very hard.
Yeah. Yes. Yeah. Yes. You will basically wash away any directional information, but also While here you can keep kind of more coherent information about where the source comes from, but is also, not a very realistic situation. We are typically in a situation where the fluctuations of magnetic field are either much smaller or kind of comparable. So diffusion is really attacked in the galaxy, and indeed we do have some basics indicators that there is a diffusive transport going on in our own galaxy. This comes mostly from two observations. So one is the abundance, the measurement of the abundance of the elements in the cosmic ray interstellar space, so farther from the solar system, compared with the abundance within the solar system. This is normalized to the carbon abundance in the solar system. So as you can see, for most all elements, the cosmic ray abundances and the solar system abundances, they do match, except for a few elements like lithium, beryllium, and boron. Those are very fragile elements with a small binding energy, which are typically produced as secondary processes. So cannot be produced, for example, directly in stellar nucleosynthesis. And the fact, and indeed you see here, there is very low abundance of these elements in the neighborhood of the sun. And so they have to be produced necessarily by what we call spallation. Namely, when you have a heavier nucleus which is propagating in the galaxy, it can interact with the particles of the interstellar medium, mostly protons, but also a bit of helium. And within this interaction process, you can produce lighter nuclei like lithium, beryllium, and boron. So the fact that you have heavy elements like carbon and oxygen with particles like protons in the stellar medium then tells you that you can form those lithium, beryllium, and boron elements at these rates through what we call secondary fragmentation or spallations. And so it means that cosmic rays should be present within our galaxy. They cannot just be produced and escape, but they need to reside in the galaxy to have the time for those processes, these spallation processes, to happen. And the same is something that you can infer with what we call cosmic clocks. Those are, as an example of this is, for example, the beryllium-10, which is an unstable element. Much more, while you have its companion, the beryllium-9, which is more stable. And by comparing the abundances of beryllium-10 and beryllium-9 within our own galaxy, you can infer what is the typical residence time of cosmic rays in the galaxy. And this is about of the order of 100 megayears. And so the point is that you know what is the half-life time of beryllium-10. Beryllium-9 and beryllium-10 should be produced at the same rate, more or less, within stellar products. And so while beryllium-9 is stable, beryllium-10 decays. So the longer is its time of residence in the galaxy, the less abundance of beryllium-10 with respect to beryllium-9 you should find. And by measuring what is the ratio between the two, you can measure on average how long cosmic rays do have to stay. So again, they cannot be produced and escape immediately, otherwise you wouldn't have seen the depletion of beryllium-10 because of simply decaying within the galaxy. So there are, the theory of cosmic ray production and propagation is really a huge topic of astrophysics, but I just want you to describe how, in one dimension, we can understand this cosmic ray diffusion process. So the simplest model that you can have for your galaxy is that you have your galaxy squeezed within an infinitesimal thin disk, which has a very small height, this small h, and the magnetic, which is embedded in a magnetic halo of size capital H, and it extends over the radius of your galaxy. So here the scale says that the radius of the galaxy of the disk should be much larger than the halo height, the magnetic halo height, which is in turn much larger than the thickness of the disk. So you can just approximate this 3D disk with just a plane. And in 1D, the propagation of cosmic rays is very simple if we only consider diffusion. So this phi here is related directly to the phase space of the space density of the particles. Is just the isotropic, assuming isotropic emission is just the integral over 4 pi and over the solid angle. Sorry, 1 over 4 pi of the integral over the solid angle of the phase space density. If you have only diffusion, the variation in time of the flux of cosmic ray particles depends on the diffusion coefficient, which alters the space distribution, as I said, because it can deflect particles, and on this source term here, which is responsible for injecting the cosmic ray particles in the medium. So this cosmic ray source term can be approximated in this very simple picture by the injection of particles in this disk at a given z. So we just assume that everything is squeezed at z equal to 0. So this is the so-called slab model, and one can solve it. I won't go into the details, but typically the cosmic radiation is, we assume, steady state, so you just get rid of the time dependence, which is instead relevant for processes which are dependent on time, like burst injections or stuff like that. And so you only have diffusion, sorry, here's a capital K, which related to, with the variation in space is related to the, depends on how many cosmic rays you inject in a given point. So you can work out the solution. Here are the steps. I leave you to just watch them later on. But the point is that you can iteratively solve this equation by looking for boundary conditions. So the first thing is that you know how that we are just assuming this infinitesimally thin disk approximation, so everything occurs in the z equals 0 direction, and you want the flux of cosmic rays just to be 0 at the boundary of the magnetic halo, because then particles escape and you don't have them any longer. And you can look for the general solution, which describes how the flux depends on the z, so the direction in the magnetic halo, and the momentum, and is related to the source term here. But besides having only the source term dependence, you can also see that there is a term which acts an effective cooling time that relates to the halo height, so the magnetic halo height, and the diffusion coefficient. So what I mean here is that if you have an injected spectrum of cosmic rays, you won't you will never be able to just see that directly, because diffusion will wash away all directional information through the fact that particles diffuse. And so the injected spectrum really differs from what you can measure in cosmic rays. And the second point is that by measuring the cosmic ray fluxes, you can infer properties on the source term, but also on the propagation parameters of the cosmic ray themselves. So there is a degeneracy, or if you want, a rich information that is contained in this cosmic ray flux that you measure at Earth. And things are more complicated by the fact that you not only have diffusion, of course, but you also have other processes that alter the cosmic ray propagation. So you might have convection and advection processes, where your spatial transport is affected by large coherent movements that there might be in the galaxy, as for example where you have very strong outflows or very large stellar winds. So you have a terms that describes how the velocity of your outflow, for example, alter the distribution of cosmic rays in space, and this is effective for wind speeds that are above 10 kilometers per second. And you also have what we call energy losses there again, which can be in certain limits adiabatic, and these are the ones that act when you are within a cosmic ray source accelerator, and you have the reacceleration of those particles. I haven't mentioned also the reacceleration term, but again, this is just to give you the idea that cosmic ray transport is really complicated, and this is only the 1D equations. You of course have to go 3D. So the way to solve these propagation equations is through rely on numerical methods. So there are numerical codes like Galprop, Hermes, and Picard, where by defining what is the distribution of sources that create cosmic rays and inject them in the interstellar medium, then you can solve these differential equations by having, for example, the real gas maps of the interstellar medium or other types of properties of the interstellar medium itself, to then reconstruct for each point in space and in time in the galaxy what is the phase-space density, so the flux of cosmic rays that you do expect. So to conclude on cosmic rays, I want also to mention something that you see often, and that is this secondary to primary ratio. So why this secondary to primary ratio is important to get information about propagation? The point is that, as I mentioned, so primaries are the ones that are producing cosmic ray accelerators or in stellar environments, while secondaries are lithium, beryllium, boron that come from the spallation. So you have primaries, they propagate into the interstellar medium, and then they lead to the formation of secondary nuclei. So the source term for secondary nuclei depends on the flux of primaries times the rate at which primaries can produce secondaries. So this, for example, depends on the cross-section, what is the cross-section of proton-proton collisions in the interstellar medium. So if you were to just look at work out the solution of the slab model by using this source term here, you can then derive the solution for the flux of secondaries. And the flux of secondaries divided by the flux of primary is related to this rate of production, so which is the probability to produce secondaries from a primary nuclei, times this effective cooling timescale that I mentioned before. So is related again to the halo height and the diffusion coefficient. So it means that if you are able to measure with extremely good precision, and this is the case with the data of IMS, for example, elements like beryllium, like boron over carbon. So this relation informs you directly about the halo height and the diffusion. So what people do when they actually look at determining the propagation parameters of cosmic rays in the galaxy, they use all measurements from IMS, because you have a great precision, is undoubtedly the most precise instrument at around 10 to 100 gigavolt rigidities. They look at different elements and the ratio of secondary over primary, like over boron over carbon, and from there they can fix, with whatever global fit technique you prefer, what is the halo height and the diffusion coefficient. So secondary to primary ratios are used to infer those properties, which later are, let's say, fixed or marginalized over when you want to look for exotic physics in other nuclei or other antimatter fluxes. And we'll see that tomorrow. So, but I haven't mentioned anything about cosmic ray sources up to here. So I've just mentioned about transport and just telling you that you have to put some source term. So what does accelerate particles up to 10 to the 19 electron volts, and are particle accelerated at lower energy any different from a particle accelerated at higher energies? So there are, of course, observations that are made with high energy instruments that measure particles up to 10 to the 12 electron volt, 10 to the 15, and they can say, because are gamma rays, so they are directional, that those are galactic objects. So we know that galactic objects can contribute up to 10 to the 15 electron volt to the all particle spectrum. And what are those galactic objects are supernova remnants, pulsar wind nebulae, and very recently also it has probed that stellar clusters should contribute to a part of the galactic cosmic rays. However, above 10 to the 15, we think that the standard, we don't know any galactic accelerator. So we think there is a transition between 10 to the 15 up to 10 to the 18 electron volt from the galactic accelerators to the extragalactic ones. And the extragalactic ones are typically particles that are accelerated in very extreme environments, like jets of active galactic nuclei, or GRBs, or galaxy clusters. And then they arrived up to us, but then with the cutoff, which is their natural horizon. So there are open questions which are related to what is the maximal energy of cosmic rays that can be accelerated, and what does this transition means and where it does occur. So to understand how cosmic rays are accelerated, let me just mention that the acceleration of cosmic rays has some minimal requirements. So the energetic should be right. So you should take energy somewhere. So either is the kinetic energy from, for example, a pulsar which very speedily rotates, or it should be gravitational or magnetic, as in the case of the solar flares. You should have some mechanism to transfer this energy and to make it possible that this particle can be accelerated and then ejected from those systems. And particles should be confined within those systems for a longer time in order to be able to efficiently being accelerated. And no, you don't have to have significant energy losses, because if you accelerate and then lose energies immediately, well, you cannot have your particle escape any longer. So we need electric fields that accelerate particles, and these are typically generated when you have moving magnetic fields. So this occurs in fast rotating pulsars or in shock waves, as for example in supernova remnants. But what is the maximal energy that can a particle be accelerated to? This depends on the confinement conditions. So in order to a system to be able to contain a particles, you need the Lermor radius to be smaller than the size of the accelerator. And there is this very famous plot, which is called the Hillas plot, which relates the magnetic field as a function of the characteristic size of the objects. And for typical objects in the galaxy or extragalactic objects, you have the maximal energies that those accelerators can reach, which has to be smaller than the product of the radius of the objects times the magnetic field. So you see that you can reach energy up to the knee for mostly all galactic objects, perhaps even to the ankle, but to go to the GZK cutoff, you really need extragalactic objects like active galactic nuclei and blazars or galaxy clusters. So what do we know about cosmic ray accelerators and how do we measure that? Well, we actually can use photons, high energy photons, to image the structure of the shells of supernova remnants. So this is the image from Hess measurement of one supernova remnant. We see also what is the luminosity as a function of energy for most of the supernova remnants in the galaxy. And what we don't see is are particles or photons above a few TeV. So there seems to be a natural cutoff, a few TeV, which requires supernova remnant to accelerate protons only up to a few TeV and not to be able to be a source of PeV particle. And why it is interesting to go to PeV is that because we have actually measured the emission of particle up to the PeV scale, and we have a measurement of the Hess on the galactic disk, where he detected gamma ray emission, mostly coming from a cosmic ray accelerator up to PeV energy. So what is that then if supernova remnants and pulsar wind nebulae cannot accelerate protons up to this very high energy? Well, the speculation here is that you would have PeV protons to be ejected directly by Sagittarius A star, so the central massive black holes in the heart of the Milky Way, that would be able to accelerate protons up to PeV energies. And what you can measure with the Hess gamma rays is how the flux decrease with distance from the galactic center. And you see that the behavior that it follows is rather 1 over R, and which corresponds well to the data, and this is typically what you would expect if you were to have this kind of process. In the last 2 minutes before breaking, I want to mention about effects which differ substantially from the non-collisional effects that I described as the diffusion transport. So the collision effect can be of two types. You can have catastrophic losses. So whenever you have the disruption of nuclei because of interactions with other particles. And here you describe those catastrophic losses with the terms of particle physics. And those are the losses that lead to the production of secondaries, for example, are losses for the primaries, but they do produce secondaries. So you can describe everything by the mean free path of a particle, which is the average distances that the particle can travel in the medium of density n before interacting. And of course, the mean-free path depends on the cross-section of the process. For example, if you have proton-protons, or if you have helium-protons, or whatever else. And the rate at which this process is effective is the collision rate, and you can directly relate the collision rate to the optical depth that this particle can travel. If you were to describe the loss more continuously, so you also have mechanisms that require you to do so, and in this case you can describe the loss of energy, so the energy divided the mean loss rate per unit time, and defining this loss time scale. So there are two very important mechanisms for continuous losses that I want to mention here before breaking. One is the synchrotron. So whenever you have a rotating charge that is accelerated, this particle also radiates because it's an accelerated particle. And the power at which this particle radiates is related to the magnetic field and its velocity and its charge. So you can describe the average energy loss in terms of the Thomson cross-section, which is the non-relativistic limit, and the mean average density of magnetic fields that you have in your environments. So here I just wrote two formula that gives you an idea what wavelengths we are talking about. So the synchrotron energy of the particles which is radiated, so photons, is directly related to the magnetic field and the energy of the primary electrons. So you see that the synchrotron is effective for particles which are light, so normally electrons. So if you have electrons of GeV energies, the magnetic field of the microgauss, as this is the case in our galaxy, you end up having synchrotron photons at 500 microelectron volts, which is about the megahertz range, so in radio. So synchrotron gives you radio emission. And the spectrum of the synchrotron emission is directly related to the primary through this 1 minus alpha divided by 2. So if you know the spectrum of the primary's electrons, then you can derive what is the spectrum of the synchrotron. So for inverse Compton, this is a bit different, because in this inverse Compton you can describe it by the interaction of electrons with photons, and you can go fully relativistic. You have the Klein-Nishina process, where you can write out the full cross-section in the relativistic regime. And again, the time loss, the average energy time loss, is related to the gamma factor of your particle and the density of interstellar radiation field. And in the next part, we will see what is the interstellar radiation field and how all this business is related to radio and gamma ray emission. So if you have questions, I'm happy to take them.
Thank you, Francesca, for the very nice lecture. Do we have questions?
Hi, thank you for the interesting talk. So I was asking that in the first image that was in your first slide, neutrinos can travel a long distance undeflected. So we know that neutrinos have electromagnetic properties. So is it possible that they can be deflected by intergalactic magnetic field before reaching the Earth?
I haven't heard of that option, but I'll look for that and come back to you.
Okay, thank you.
Thank you.
So my question was from actually this figure. So in the region of highest energy and the distance around the nearest galaxy, there's a window that we can see. Do we expect to have any source of such high energetic particles that we can see, or have we seen it?
Yeah, so this is one of the main things. If you were to find particles above the XXXIII cutoff, then you will be exactly in this spot. So for example, the Pierre Auger telescope is really trying to push. I mean, to try to collect as many particles as they want. So it's very important to actually be able to claim detection of this very high energy. The same is true for neutrinos. You really want to see neutrinos that would come from particles that are detected, are produced in this open window here.
Hello. I don't know if it makes a lot of sense, the question, but so you said that the maximum energy that can be introduced, to what can be accelerated a cosmic ray is given by this, the size of the accelerator times the magnetic field. So, but do you measure the magnetic field directly and then infer that maximum energy, or you infer the magnetic field with the maximum energy of the cosmic rays that you see?
So typically you can, so here we are talking about charged particles, and what you can do to measure the magnetic field within the source is to look at mostly synchrotron radiation. So you look at Faraday rotation, for example, for pulsars, but also supernova remnants, or polarization. So this is kind of, again, going back to cosmic rays, because cosmic rays are the source of everything, of whatever multi-wavelength emission we see from this kind of objects. But there are, so the way in which wavelengths are connected allows you to break some of these degeneracies. So, for example, the Faraday rotation is only related to the electron population of those accelerators. And here, those accelerators mostly, the electrons that are produced as a secondary, as a final step or final products of the proton accelerations. So we can think of the synchrotron as something that measures only magnetic field, or the polarization as something that measures only magnetic field, although the links with the primary proton population, of course, is there. And this is a very simplistic way to understand the picture. But you can actually work out magnetic field, maximum energy, and confinement radius if you were to combine in what we call the multi-wavelength model of the accelerator, different informations. You can think about particle physics. You can have those global fits where you get different informations from different observables, and here is the same. You can break the degeneracy by using a multi-wavelength approach to the problem.
Why do you work in rigidity when you compare primary to secondary cosmic rays instead of... I would assume that the energy is shared per nucleon, not per...
Yes, so you can do the two things. So either you work on energy per nucleon, or you work in rigidity. And rigidity is a bit more precise, in a sense that if you use the data from AMS, for example, you measure really charge over momentum, momentum over charge. This is the measurement that you have directly in the detector space. So if you don't want to correct for instrumental response function or just partly for it, you go for rigidity space. It's just a way in which you want to relate to your instrument.